The unique construction of the Spirotherm air and dirt combination separator allows for the removal of both entrained air and dirt particles. The patented Spirotube, the core of the unit, not only removes entrained air, but also countless microbubbles. Air in the system water can cause corrosion, reduced efficiency, poorly heated or inadequately cooled rooms, accelerated component wear, and ongoing complaints. The air bubbles rise and collect in the air chamber before they are vented from the system via an integral automatic valve. Air problems become a thing of the past. Spirotherm is capable of scrubbing 100% of the free and entrained air and up to 99.6% of the dissolved air, making the water absorptive throughout the system. All while the air is being eliminated, the patented Spirotube causes dirt particles of all sizes to sink to the bottom of the unit and collect in the dirt chamber, eliminating any blockage concerns. Dirt can be flushed through the provided full port ball valve while the system remains fully operational. The large dirt collection chamber ensures infrequent flushing. Because the dirt is collected outside of the main flow path, blockages do not occur and Spirotrap pressure drop remains constant. Independent research has proven that Spirotherm combination air and dirt separators are capable of removing debris as small as 5 micron. The benefits of eliminating air and dirt are energy savings, increased energy efficiency, reduced operating costs, protect critical system components, improve system reliability, all while minimizing the owner's total cost of ownership over the life of the system.
Well, good afternoon, everyone, and thank you for joining us for today's webinar. I'm Sam Schwartz, and I'm a Member Engagement and Marketing Manager for EMA. I'd like to go over just a few quick housekeeping items before we get started. We encourage you to submit questions at any time using the Q&A button on the bottom part of the player. A few will be selected at the end of the webinar. Hopefully we can get through all of them, and if there are any left unanswered, the speaker will attend to them afterwards via email. The chat function is where you can make general comments and chat with attendees. If you happen to be experiencing technical problems during the webinar, please use the chat function to inform the panelists. And then finally, in terms of continuing education credit, you will receive an email within 1 week with your proof of attendance. Today's webinar is revealing hidden costs in hydronic cooling and heating systems with your speaker, Stephen Clinton. A little bit about Stephen. He's a professional engineer, a LEED accredited professional, and a previously certified medical gas inspector who designed and managed the design of healthcare, research laboratory, and higher education projects throughout the United States and China during his 19 tenure as a consulting engineer. Multiple higher education projects, which he designed, achieved LEED, Gold, and Silver certification. Thank you again, everyone, for joining us. And with that, I'll hand it off to Stephen to kick us off today. Stephen?
Thank you, Sam, and thank you, everyone, for joining us. Good morning to those on the West Coast, and good afternoon to everyone else. We know your time is valuable. We have an hour, so we're going to try to cover a good bit of information in the short time we have. And again, thank you for joining us. As Sam said, I'm with Spirotherm. We're celebrating our 30th year. We're the world leader in high efficiency air and dirt elimination for hydronic systems. This is all we do. We remove air, we remove dirt. We've been doing it for a very long time. Now we have a number of people in the audience from different parts of the country, different industries. So if you would, help us answer a couple of poll questions. How long have you been in the industry? And then also, what's your role? That'll give us a good idea to know where people are coming from, because we know that there are people that design systems, operate systems, own systems. So yeah, if you would take just a second, if you don't mind, and answer the poll for us, we would really, we would appreciate that, as that will give us a chance to maybe better tailor some of our discussion. So that was the first part of the number of years you've been in the industry. The other side is, what is your role? So as we go through this, again, we're going to try to be very efficient with our time, but hit a lot of information. If you have questions or comments, you can send those through and we'll try to get those at the end. We're going to hit a number of topics today. Some of those that maybe Spirotherm customers may have heard some of these discussion points before, but we're going to share some new things with you. Basically, we're going to take it from what does air do in a system? How does it affect a system? To what is dirt? And then basically traditionally in our industry, how have we dealt with it? And then what are some of those costs? You know, sometimes we may think there are certain costs. Okay, we understand how that affects things. But there are a lot of other things we may not in our industry have really looked at, or there may be things that we've looked at over the years and we thought, well, we just have to live with it. So we have one of our customers on the West Coast that said something a few months ago that was great. He made a point. He said, Stephen, not only have we decreased our differential pressure in our chilled water system by 35 PSI, and he goes, I've been running this plant for 25 years. He said, but also you've given us a new normal. So maybe we're going to talk about some new normals that you may want to experience or maybe not have thought about. We're going to talk about the benefits. We're also going to talk about if we don't address air and dirt, then basically who bears the cost of that? Which team members, because this whole design, construction, operation is a big team. And then basically who benefits if we effectively remove air and dirt. So we're going to jump straight to the point. I'm an engineer. I like to get to the point. Let's deal with data. Let's deal with information. We're going to talk about three main aspects of air in a hydronic system. It's not a good thing. One, it causes corrosion. Our industry, yeah, we're pretty used to that. We give a head nod to that. We understand it, we deal with it, but more often than not, it's throw some chemicals in a pot feeder and come back a year later. That's not a good thing. More importantly, oftentimes from an energy perspective, and one of the most significant aspects is it reduces heat transfer. We're going to get into why that is, but we need to think about that because that is probably the most important thing. If you don't walk out of this discussion today with anything else, walk out with that. It's really important to know. The other thing is it reduces pump performance. We'll share some industry data that comes from 3 different pump industries or resources that aren't Spirotherms to tell you how just a very small amount of air in a system can dramatically increase pump energy and reduce its performance. The first we're going to hit is corrosion. You know, what is corrosion? Corrosion is basically rust. When you have oxygen, 20% of air is oxygen, it causes rust. That causes magnetite. You're hearing a lot of that in discussions, especially with some of the boiler manufacturers. There's not just rust, and there's magnetite, hematite, there are other particles. We need to let all of those separate out of the system. So corrosion is something we're probably more used to than some other things. The other thing is, when you look at corrosion, does that look familiar? That's actually a customer we met with not too long ago they're having issues. Their systems look like tar. Is that something that you've probably seen? Well, that's corrosion. That's really a significant thing to consider, especially because in this case, their chillers are cooled by the chilled water system. The filter on the left is actually the filter that serves their main chiller. And if it clogs up and goes down, this healthcare facility has some issues. All right. My boss likes to say that I can be a real geek. So I'm going to go geek mode on everybody. Basically, we're going to go back to heat transfer. And we're going to look at that. When you calculate that, that's the mass flow rate of the fluid times the specific heat of the fluid times the temperature differential. In our industry, we've kind of done that down to, the rule of thumb is 500 times the gallons per minute of flow times the temperature differential. Where that comes out to is that's basically 1 gallon of water with a 1 degree temperature differential, about 499.8. So everybody's rounded up. You see the red asterisk there. That's very, very important because the red asterisk tells us that assumes an air-free system. Every load calculation program, every piece of software used to size every piece of equipment out there. And I was in the rep business for 3.5 years as well. So I repped about 40 lines of equipment. It assumes an air-free system. Well, what's the difference? Why is that significant? Because air negatively impacts heat transfer. Air is an insulator. And if you have a fluid air mixture, basically air mixed in with your fluid, no matter what it is, that fluid cannot transfer heat as effectively as the homogeneous fluid itself, for which the entire system was designed. A few years ago, when I started looking at this, I initially looked at the specific heat and thought, hey, water is 4 times that of air. So that's really what I'm going to key in on. But then as I thought about it even more, I thought, wow, the big difference is the mass flow rate, because water is much more dense than air. I think 840 times more dense. So basically, if I have 1 gallon of water, that's 8.33 pounds. 1 gallon of air is 0.0106. So basically, that is not transferring very much heat at all. So basically, again, it's an insulator. If you had 5% of air in your fluid, that rule of thumb, 500 times GPM times delta T is roughly 475, 10% and so on. It's a big deal. Now, if you have heard about the 3 forms of air, then okay, you probably will nod your head and go, okay, I remember that. Some of us who may not be familiar with it, this may be something new for you. There are 3 types of air you run into in a system. Free air, when you fill the system up, it starts off dry. You have to push the air out of the way to make room for the water. That's what high point air vents are for. They allow you to push the water out, or push the air out to make room for the water. Invariably, you get little pockets up and down where water gets caught. Now, when the pumps start, those air bubbles are pushed along. They stay in the coils, they stay in the high points. The other bubbles start being pushed throughout the system. Oftentimes they end up at the highest points, penthouse mechanical rooms, air handling units and mechanical rooms at the furthest end of the system. You have noisy flow, you have bouncing pressure gauges. The other part is dissolved air, and dissolved air, oftentimes we don't think about that. At a presentation a year or so ago, a little term came to me, the often overlooked offender. And we need to think about that because this is very important. Let's look at it this way. Let's look at it and say that every gallon of water that you bring into a system, let's say that you fill that system up with 60-degree water at 60 PSI. That water, per Henry's law, which says the amount of water the amount of air that water can hold in solution is directly related to the temperature and pressure. It can hold up to 10.4% by volume of dissolved air. However, let's say we take that water and we don't change the pressure at all. All we do is we heat it up to 180 degrees. Well, I'm going to go to my cheat sheet here, drops it down to 5.2%. So what's happening is that fluid physically cannot hold air in solution. So oftentimes if we think about heating hot water systems that typically clog up and get dirty and tear up equipment, oftentimes that's because all that air comes out of the solution, gets pushed around, gets pushed back into solution when it hits the pump. We'll talk some more about that in a bit. How do you get air in a system? We had lots of discussions, possibly with some of you on this call and others who've said, okay, I have a closed system. Well, okay, you get initially the system fill air, but also too, if you can't get to your manual air vents or some of the other automatic air vents aren't working, you're still going to have air that's there. I was just at a facility recently and we talked to some folks and they said, hey, what happens every time we bring on this new bank of equipment? What happens? Well, typically they said the contractor it would be dry pipe and they would open up to the central chill water system and then it would go. That's introducing raw air to a system, not even dissolved air. So oftentimes you have leaks in systems, you're making up air. A closed system oftentimes is really not truly closed. There's new air coming in different ways. All right, we're going to talk about, so what if we have air in the system? What difference does it make? Well, the first part we've already talked about, we've shown you some examples that systems corrode. Air is 20% oxygen. And so if we do that, how do we combat that? Oftentimes it's chemical treatment. Sometimes it's not, but proper chemical treatment can help It can help the rust, but it cannot address the issues with heat transfer because, as we've already talked about, that air is an insulator. It's affecting the ability of that fluid to transfer heat. Well, think about it. What does that fluid touch? Let's say you're in a chilled water system. It affects the chiller, the coils, heat exchangers, affects everything in the entire system. Same thing for a heating hot water system. Those that in the different parts of the country that are familiar with glycol will probably get this immediately, because if I were to come to you and say, I'm taking a water system and turning it into a glycol system, you more than likely would just go time out. Don't do that, because you just derated every piece of equipment in the system. That's really what air is doing as well. The other thing is you increase the pump energy. Why is that? Well, we're going to show you some documents in just a second, a few slides down, that talk about that. But essentially what's happening is the pump is only designed to pump water. It's not designed to pump water and compress air at the same time. That's really what it's doing. It's not made for that. Now, why would this be the case? Well, think about it this way, especially those of us in the South or other places where we deal with humidity all the time. If I'm trying to get 52-degree discharge air temperature off of a coil, but let's say I have air in the coil, and I'm only getting 60 degrees, well, I need to account for that heat transfer. What do? I have to increase the supply fan energy. It's a heat balance. So inefficiency on the water side affects the air side. Supply fan energy is much less efficient than pumping energy. Something to consider. So basically, what may have been overlooked all these years, there's just air in the system. It's having a very significant impact on your energy bill. We'll get into a little bit of that later to tell you how much and do a little quantification of that. So basically, air in the system that some of us may have lived with over all these years as business as usual, it's having a dramatic impact on the OPEX, operational expenses, and CapEx, capital expenses for a project, but it's also affecting everybody involved in that project. We all need to think about that. We'll talk about that here a little bit later. How do I know I have air in my system? Well, think about it. If you walk through a mechanical room, not even a mechanical room, walk through a school or a hospital or a research lab or somewhere. If you walk down a hallway or in a room and you hear if you hear a flow noise above you in the piping system, that's not water, that's air. Because unless water is superheated or at very high velocity and pressure, it's not going to make noise. So that's air that you're hearing. The other thing is, if you walk into typical mechanical room and you see pressure gauges, they're fluttering, they're jittery, they're bouncing. That can't happen with a non-compressible fluid like water. But if air is having micro pressure changes, that's why you get that. We oftentimes think about cavitation only in a conventional water system. We can have that in a closed system as well, because air at the impeller is causing all kinds of issues. The next two are interesting because there's something that this is business as usual. Why is that? It's system effect. It's some other cause. And granted, there can be all kinds of issues and reasons why a pump curve may not match the pump data, why chillers, boilers, heat exchangers, coils don't meet their design criteria. But oftentimes, because I was sat in the same chair a lot of y'all do, on the consulting side, you wonder, why is this not matching at all? Well, there can be error. Someone could have just flat out lied. They could have just put some numbers down. But we have a lot of case studies that have shown that after removing air from the system, primarily in the dirt too, you see the system operating the way that it's supposed to. We see that too in low system delta T's. How many times do you have a project? You're designing a new one, you have an existing one, you're trying to get a project started, it's not working. Well, what do? Well, think about that. If you're looking at energy and my fluid's not the right fluid, something has to give somewhere. These are three of those documents that I mentioned earlier. The Gould's Pump Manual on the left, the Centrifugal Pumps Handbook in the middle, and then the Labor Tabor white paper all reference very similar data. And what they say is a mixture of only 2% gas, basically 2% entrained air in a fluid, which is not much, can reduce pump performance by 10%. Just 4%, just double that, which is a very small amount of air relatively, can affect pump performance by over 43%. That's not Spirotherm, that's the pump industry. Something to consider. Now, in our industry, we've tried to take care of air in different ways over the years. The thing we need to keep in mind is for many, many decades before VFDs really came in vogue 20 to 30 years ago, every system had to operate constant flow because everything was you had three-way valves. You had to flow all the water all the time. You didn't have the benefit of being able to reduce and vary flow. So there were certain pieces of equipment. Two of the most, the most prevalent ones were air scoops. Hey, we allow some of the air bubbles to be removed. And traditional air separators. Now, it's gone from the original iteration that had a small perforated dip tube to the current versions that basically there's really not anything in there. You have the stainless steel strainer, that's really more to catch the cats and the squirrels and the welding rods that get caught in the system. But there's not much there for the air to collect on, to be removed. One thing I remember when I went to pump training early in my career, many years ago, I remember looking at this thinking, why would I design an air removal device that pushes the water in, swirls it around, and removes the water out the bottom rather than the top? Because those bigger bubbles can actually make their way to the top, but it's the small bubbles that don't have the buoyant forces to overcome some of that flow. So I remember even then, even before I knew about Spirotherm, I thought, let's think about that. So that's how typically our industries looked at things, say that's how we're going to remove the air. But 50 years ago, Mr. Rolfsen in the Netherlands created and invented the first spirotube element, the first coalescing air and dirt separator. It's really neat that we work for the company that created an entire industry. There were no coalescing separators anywhere until he invented that. Did that in the Netherlands 50 plus years ago, and we're celebrating our 30-year anniversary here in the United States for North America. How are we different? What we're different is that we're not spinning. We're not trying to use centrifugal force. We're doing the opposite. We want the water to come in. As you saw in that introductory video, I want to include that one. So there are certain things you were able to see graphically that typically, if you were in a presentation in person, you would see it at the demo unit that we have. If you've ever been by our booth at CX Energy or other conferences, we have a demo unit that you can see air and dirt being removed. But basically, we're able to remove air and also dirt by slowing the velocity of the fluid, suppressing the turbulence, and we want the opportunity for those air bubbles to have to come in, slow down, and the big ones to rise to the top. Also, in the next slide, I'll show you that the coalescing, the reason why it's called coalescing is the small bubbles like to grab the little edges of the copper fine filaments, and then other bubbles grab others, and as they get more and more, they rise to the top. What happens is, and you can see this when you watch the demo, is we can put an air bubble in a free air pocket. The water literally becomes absorptive. It enters the unit with more air than it leaves with when it goes back out into the system. It scavenges all that air to come into the system. All right. So yes, someone had asked about the air scoop. So that's an air scoop that's been in the industry for a while. So basically, we're doing the same thing. We are removing the air. We can remove 100% of the free air, pockets throughout the system, all the entrained air up to 99.6% of the dissolved air. That's the point of low solubility. So if we're at that point of 180 degrees and 60 PSI, 5.2 is the smallest amount of air that can be dissolved. We can remove 99.6% of that. So basically, we're unsurpassed in what we can do. We're also very effective in glycol solutions. Glycol is typically very difficult to deal with. It causes foam, and that foam basically is harder to remove air bubbles and also holds dirt. I thought this was a good slide, something you might like to see. This is a unit that's a 30-inch pipe connection, 60-inch shell diameter. That handles a lot of flow, but what you'll see is all of these units, all these elements here are the spiral tube element that you saw earlier, which is basically a whole lot of these. So there's no, when the water comes in one side and goes out the other, it has to go through this, air and dirt both. One of the, if you can zoom in or if you can see that, you'll notice on the bottom of the float there are air bubbles here. You can also possibly see small air bubbles here as well. They're coalescing. That's where the heavy lifting is done, because it's those very small bubbles that over time collect others and are removed. Now, because we deal with, people ask us, hey, what's a comparison? How do you hold up against a regular separator? I've been specifying those for decades. Why should I change? What we did was we mocked up a system and we said, let's put one unit in series with the other, put a traditional air separator in line with ours, run it for a period of time, measure the amount of air being removed, swap it, do it again. Let us be first and let them be second. We want to share that data with you, because what we found was, all right, the first unit, the traditional air separator, is able to see the big bubbles first. So it's able to remove them each pass, and then we're removing air as well. So for the first hour, we're both removing air, and then still happening a little bit on the second hour. But watch what happens when we get past about that first hour and a half or 2 hours. The traditional separator basically flatlines, and we continue to remove air. The difference is even more significant when you look at what's happening if we get first crack at the air. Why is that? Well, again, you're saying that our unit comes through, the air bubbles rise to the top. In this case, water's coming in, pushing down, air bubbles are having to fight against that. Also, too, there's not any type of a coalescing media that helps the removal of the air. So we have that. So what happens if we have oxygen? Why should we care? Well, some of these slides may look familiar to some of you. Dirt and all the junk that happens with it. Dirt oftentimes is really, some of it's biological, some of it's truly dirt that's got into the system. But oftentimes when you say the term dirt, that oftentimes is fine metallic debris. It's basically rusty material. What's happening when that's flowing through a system? It's essentially liquid sandpaper. It's metallic, small metallic debris zipping along at 10 feet per second. Well, let's say it gets into a pump seal. How many times have you seen pump seals go down? Or control valves. Earlier in my career, we saw lots of globe valves. And you would see globe valves failing all the time because they're getting scored. As the seat tried to close, it would just scour it and it would be destroyed. Well, a lot of that is because that fine debris is 30, 40, 100 feet per second. So that dirt is not doing anything to help the system at all. So how we typically looked at that as an industry? Well, there are different ways. Oftentimes these are catch and hold methods. They're filtration, or they're strainers or filters. The first type is just the strainer. Strainers are good, especially for catching big things. But when you get into small things, they start to load up, and it can be good. It's like an air filter on your house. The more it loads, the better it works. But what happens to the pressure drop? It goes up significantly. That affects your pumping system. The other thing is, oftentimes, how many of those strainer baskets actually are ever serviced? Probably not a whole lot. The other type is, basically one of the side stream applications are bag filters. You come in, you flow through as a single pass. We've talked to some different customers, and you might have $100 or $150 a bag in each of those assemblies. So you could be looking at several $100s or several $1,000s just to change out the bag filters in a single assembly, and the pumping energy and blow down and all that. The next type is, again, typically in a side stream, is a sand filter. Sometimes you see this more in condenser water systems or open systems, or maybe there's a chilled water system. People are trying to get down to really small particles, maybe a half a micron or a micron. Well, in our industry, typically what we find is if you look at various materials and various reference guides, basically the 10 to 75 microns oftentimes is really where you're having the most fouling of coils and heat exchangers. The American Drinking Water Foundation says that basically if you get down to around 5 microns or smaller, that's really stuff that a biocide can handle. We get down to 5 microns over time we'll tell you about in a second, in a closed system. Basically sand filters work pretty well. They can polish pretty well, but oftentimes we see them 6 months to a year in, they turn into like concrete sometimes, if not properly maintained. Another type you see is, the cyclonic separator. It spins, it uses centrifugal force. Typically, you're looking around 70 to 75 microns, specific gravity of 2.5 or greater, unless you go with a separate solids recovery vessel, which is basically a bag filter. Oftentimes, those come with a separate pump, side stream, so you're only seeing part of the flow, part of the time. So that's one way it's been dealt with in the industry. And how are we different? Well, in our case, we're looking at full flow. What you're seeing here is this is a dirt separator, and this is a dirt only separator. It's exactly the same unit as the air and dirt, but there's no air removal side. So we're using the same principles of reduce the velocity, reduce the turbulence, let the dirt particles come and bounce around and let gravity pull them down. The other thing that's important is we separate. We don't filter, we don't strain. If you filter and strain, high pressure drop initially and grows and gets greater the more it loads up. We don't see that. Nice thing for us is lots of third-party data and other millions of installations worldwide that basically show we remove 80% of particles 30 microns and larger after just 100 passes through the separator. In systems over time, we've been shown to get down to 5 microns. 8 microns is a red blood cell, just to give you an idea. Now, one of the most important things is you have to blow this down. I did go on a job site one time. Someone said in a meeting, well, I've had one and I can't get anything out of it. We went to look at it. It was up 12 feet in the air and no piping connection to it. And I said, when was that unit installed? 2007. When's the last time it was blown down? 2007. That's a problem. So you do need to blow it down. Every unit that has dirt removal capability has a manual, ball valve, but we recommend an automatic or maybe a constant. I really like this approach here, especially if you're looking at a unit that's maybe 12 inches or larger, especially the bigger units. You blow the water down, you have to make up the water and chemicals and things like that. This is a system where you take a very small fractional horsepower motor, you pump through a single sleeve bag filter, the water continually flows through the unit. It's great because it is truly a closed system. The nice thing too, for you owners out there that may be participating with us, you can see a DP, so you don't have to change it until your pressure drop gets higher. Also, if a project has just come online, it was supposedly flushed and cleaned, and all of a sudden you get a bunch of junk in the system, you can hold that and have a meeting with your friendly neighborhood contractor, say, hey, can you help us here? Because here's what we've just now picked up in the system. So definitely recommend some type of a system like this. Some prime examples. This is a middle school in Florida. This is just 1 week's time that it took to clean the system up. This was in a university in 2 weeks. Basically every year they would blow their system down and then it would come back to this just in a short period of time. This is in 2 weeks of how we cleaned it up. The other thing is we've talked about glycol. This is a glycol. It took 5 weeks at a church in Ohio. This is all the debris that was removed from a chilled water system at a university. This is one that's one of my favorites. This is 75 days it took to clean the system out. Our rep actually had a PO in hand for a good sized PO to replace all the piping in the entire building. And so what they had the opportunity to do is they had the opportunity to replace all the piping in the building. And our representative said, no, let's put our unit in. let's clean it up. This was the one of the boiler connections. A couple of those other pictures you saw earlier with the completely clogged runouts, that was from this project. We were able to clean that out. So we remove air, we remove dirt. Now, some of you are in different parts of the industry, and one thing I'll encourage you to do is to think of this about for a retrofit application. This is at Youngstown State University. It was a university. They'd done a performance contract, no air separator originally. After the performance contract, new chillers, variable primary, everything should have been working great. They were still having the issues in a system that was over a mile long. Over a long weekend, they took this unit out, they installed our unit. That's all, the only change they made. Everything was clean, everything was operational. There's data that we can show you. We have lots of other things we'll be happy to come share with you in person or do a webinar for you and your colleagues. But we want to hit a lot of information, and we can dive deeper in the future with you individually if you would like. But basically, this chilled water plant grew in capacity over 15%. It went from 2,300 tons to 2,700 tons at the same flow rate after this unit was installed. The engineer that was at that university went to University of Akron. Very similar thing happened. Larger system, very, very similar. So we can retrofit. The nice thing too is short radius elbows are fine. Traditional air separators are supposed to have straight runs of piping. We don't have to have that. The other thing is Kansas State University, these are big guys. Those are 20-inch pipe connections to give you some frame of reference there. Nice thing too is there are 2 future units slated. One thing I wanted to show this to you because these short radius elbows are perfectly fine. This is also something too that the owner and the engineer said, if we're going to get something in it, maybe a grocery bag or some debris from construction, it may get caught right here. Well, this is the isolation valve. This is a blind flange. Isolate the unit, swing the flange down, remove anything that's fouled it, and then move along. So new construction, retrofits works very well. All right, we have a tremendous amount of case studies. This is just a very brief listing of our case studies. And again, we're not going to delve deeply into these because we don't have time for today, but we'll be happy to follow up with you. But a few things I want to highlight. These are just some of the things that some of our customers have reported to us. This is not our data. This is our customers that have reported this. Picked up chilled water plant capacity over 15% simply by removing air. Reducing pump speeds by over 20%, which is a cubed relationship to power. One of our universities, as I mentioned earlier, said they have reduced their DP, differential pressure on the chilled water system, by 35 PSI. So you see all these things. This is real money. One of my, for many years, I worked with Vanderbilt University. I'm in the Nashville area. And their former university architect was a great guy, and he's since retired, but he used to talk about, when we would talk about money, significant projects and money, he would jokingly say, this is, my grandmother would call that folding money. So this stuff here is folding money. These are all significant things. So we worked with some of our customers to say, let's find a way to be able to look at money. How can we analyze the impact of that? Because we're trying to look at costs. And we said, one way to do that, to analyze cost savings, is to focus on energy. So what we did was, we were looking at the healthcare market at the time. So we mocked up a hospital, and we put it in 5 different cities. And we picked up that same model, we moved it around. We only changed things to make sure that we were ASHRAE 90.1 compliant. And we said, let's look at some things and let's use case study data. Let's look at the inefficiency, but kind of back out the inefficiency of air, and let's see what that does for us. Let's see the energy impact of simply mocking up having air in the system. So when we did it, we want to make sure that we hit most of the climate zones. So we're in Nashville, Boston, Tampa, Phoenix, and San Francisco. So we hit the majority of the country. Our customers were in all those different locations. Again, we'll be happy to sit down with and go through all the data, but this is what we came up with. was that what we found was when we modeled that, we went from a system with no air in the system, modeling it to case study. We found that you would be paying a penalty of 12%, plus or minus a point or two, on the chilled water side and on the heating hot water side as well. On the simple payback, that led to 2 months of discussion. This whole thing took about 10 months. But we looked at it, we said, let's look at simple payback, because as we talked to different customers, this is an installed cost, because there can be so many wide variations of that. I said, let's look at the premium cost of putting in a Spirotherm high velocity air and dirt separator that gives air and dirt removal versus a traditionally undersized traditional air separator with no dirt separator capabilities. And so that's how we came up with the very quick paybacks. Now, wrapping this up, because we want to give you time for questions and answers, kind of a cost benefit analysis. It's important to note that air and corrosion impact the entire project team. And this is something maybe that, as I've talked to customers and others around the country over the last few years, some things have come to light. So these are some things to think about. If you're a system owner or manager and you're trying to get your system open, what happens right before substantial completion? Everybody's running around trying to bleed air, trying to get things started. How many times are you delayed? Happened all the time when I was on that side of the business. That's just part of the business, part of the beast. But delayed openings, that oftentimes turns into lost revenue. You got customers who are not happy, especially if you're trying to do a retrofit. You have increased OpEx costs, operating costs, because you're more energy, more maintenance, more replacement. You're dealing with all that stuff. You're having to spend more man hours than you thought. The other thing too is capital expenses, because you're having to spend more on new equipment or to do things that you really shouldn't have to, because of a lot of that could be to air in the system. Similar to the people that operate systems. How many times, as one of my colleagues likes to say, we have unscheduled routine maintenance. It always happens at 2 a.m. on a Sunday. Things like that, or premature equipment failures, or too hot, too cold calls. You have air in the system, you're trying to chase it down. You've got people that you're dedicated. Those two guys, all they do is chase problems. And they're dealing with customer complaints as well. When you get into the contracting side, contractors, the generals, the mechanicals, the test and balance guys, and commissioning agents, you're chasing air. You're trying to get that stuff bled out. You're getting inaccuracy in some readings. You're getting headaches. Everybody gets at each other's throats sometimes. The other thing is, how many times do I go to a project and you see a bunch of punch list items that happen because people are damaging ceilings or trying to get to make manual air vents, things like that. You're chasing air. Also, test and balance and commissioning reports. The engineer reviews it, the owner reviews it, things don't look right. That costs everybody, especially the contractors and the commissioning agents, a lot of time. So when those things happen, that ends up causing meetings, probably even in the COVID world. You're spending a bunch of time, okay, let's get together, let's jump on a plane, let's fly to California or wherever. How many man hours does that burn for the contractor and all the other folks on that side, on the design and build, the construction startup side? And then all those hours, all those expenses, they eat into your profit margin. The other thing is, and how many times do we see that things happen? Sometimes they don't go to lawsuits, but how many times do you get just on the cusp of it, and then an owner or others say, we're just not going to work together in the future? And sometimes that is starting a system up causes issues. The engineers and the architects, time is money. All architects and engineers have to sell is time. And oftentimes they run out of money at the end of construction administration. And so if there are issues that come up, even if it's not even their issue, even if it's a construction issue, they get dragged into the middle of it. And so everybody turns into, let's get this thing fixed. Owners saying, I need a team approach. That's what you have to do. That costs money. The other thing is, if you're dealing with value engineering, this is kind of for the engineers, but also listen, contractors, the value engineering side, if you save a few $1,000s up front and you get rid of a Spirotherm unit that removes the dirt, removes the air, and keeps things from going south, you save a few $1,000s, everybody pays a lot more when you start getting issues. We'll show that in a second. And again, damage reputations and relationships with owners and others. From the rep side of the business, I was on that side. Now I'm a manufacturer side. I've also been on the manufacturer's local reps. If things go wrong, it's the equipment manufacturer's fault. That's the perceived notion. And also the reps have to jump in there and spend a lot of time and energy. Again, damage reputations and relationships, eat into profit margin. And then sometimes you have to replace equipment long before you should have to. So those are some things to think about that may not be on everyone's radar. So who benefits from an air and dirt-free system? As we just talked about, everybody in the project team. Air separators, especially in a coalescing air and dirt separator, oftentimes has a big target on its back because a 30, 36-inch unit on a large project has a couple of zeros behind it. But those zeros can end up switching to your column in a bad way later in the project. The last thing to think about is, and this again is part of what we provide as a service directly to you as customers and through our reps, and we work with our reps to provide this to you, is we look at this from a financial side, and we can help you put together some proposals to help you internally. If you're an owner, if you're a contractor trying to say, hey, how do we justify this? We can help you with that. One of the most important things to look at is you have to look long-term and look at the financials. The single thing that drives a lot of financial people crazy is not just to look at simple payback, because there's a lot that simple payback does not even take into account. It says, okay, simple payback, that's a quick metric, move on. These are actual two different things we've talked to customers about on two different projects. One is, this is a customer that has side stream filtration. They don't have any means of air separation, essentially. And so we're looking at it and saying, okay, let's look at the dollar signs. This is actually money you are spending to install those cartridge filters or bag filters, whatever they are. And every year, every month, however often you have to replace them every 20 years, it's a sunk cost. And the reason it goes up is because there's inflation, 3%, 2%, whatever you want to use. So you're removing dirt, but more dirt's always coming because you're not effectively removing it. On the other side, this is another customer we've talked about saying, hey, let's put in one of our units, a good size unit, at this particular project. And then let's see the positive side. You have a sunk cost, but then you also have a cost. Since our units, we have units that have been in operation over 20 years, you're going to be paying, it's going to be paying you back every year as long as it's in existence. This is reduced chemicals, reduced other costs, reduced energy costs, things like that. So think long-term, think financial, don't just look at simple payback. We'll be happy to work with you and help you in that regard. I was trying to leave a few more minutes, but you have 9 minutes. Again, we want to respect your time. Thank you for your time and attention. We'll be glad to answer any questions. Sam, however you want to handle that, then I'll be happy to answer questions.
Okay, thanks, Stephen. So we have about 4 questions that popped in here. And
Okay.
if anyone attending has more questions, just use the Q&A button and we'll try to get to them. First one, is there any concern of the AD separator getting gunked up? Should we put a DP sensor across them?
Good question. One of the things about it is, a nice thing about the separator is we don't need a DP across it because our pressure drop doesn't change. If you're a filter or strainer, you're catching and holding, fluids come through, dirt particles fall to the bottom. We do recommend that, let's say you're in a condenser water system or you're in an existing closed loop system that has a bunch of dirt and debris, or concrete line pipe or other metal fragments, that you put a strainer upstream of it. We have one customer, it's a large university, they have a bunch of large units, and they did that. We went through a lot of discussion. They put a strainer upstream of it with holes that are 3/16 of an inch in diameter that catches the big stuff, lets us do our job with the smaller things.
So this is slightly related. In
Yep.
what cases do you decide if you need just a dirt separator or a dirt/air separator?
Good question. Any Any closed loop system, I would definitely recommend the combination air and dirt separator. Because if you only, on a closed system, if you only remove dirt from the system, the air is going to cause additional corrosion. If you're an open loop system, let's say a condenser water system, that's where we typically see just a dirt only separator. However, we have customers who have so much air, especially one particular one, 60,000 ton chiller plant, the coolant tower basins were only 18 inches in diameter. So they were vortexing so much air and they wanted to look at using an air and dirt separator. But typically dirt only separator, we see that primarily in open condenser water systems.
Okay. During seasonal startup of a heating system, could air in the system result in excessive pressures? And they put in parentheses, overload expansion tanks.
That's an interesting point. I believe that it could. Sometimes what we run into is similar to that is worked with one customer, large campus, and we were there and they said, hey, on these 3 different buildings from about the 10th floor up on each of these buildings, we don't get any flow. We're actually drawing a vacuum. So what can happen is in a case like that, you literally can get large pockets of air at certain, especially the high points of buildings that basically act as a big cushion. I've not seen it as an issue where it has an issue with an expansion tank, but that's something to think about.
Can air entrainment be mitigated with an expansion tank as well?
No. The expansion tank, especially the 2 different types, and this is something, a little segue or just a little side discussion. If you have a system that has an old metal compression tank where the air is vented into the top of it and you install a spiral vent, you need to swap that out and put a bladder type expansion tank because it will remove the air from the system. The expansion tank is really more to allow the water to expand and the system to expand. It won't remove the entrained air as much because the entrained air needs somewhere to go. And oftentimes there's just a small pipe that goes into an expansion tank. So it could possibly, I just don't see how that would really have a big impact.
Okay. This next person asking if the webinar is going to be available as downloadable unit. This webinar the recording will be available on the EMA website. They said that they might like to include this webinar in a concept document that will predate a new build campus hydronic system preliminary specification. Stephen, I would guess they would reach out to you on your email address there. That'd be great.
We'd be happy to discuss that.
Great. And next question, how critical is placing the AD separator at the point of highest system temperature?
It is very important. The two of the most significant aspects of air and dirt, especially air removal, are temperature and pressure. So what we're looking for is we want to remove that air at the system where the water is warmest and where the pressure is lowest. So, and let's say in a chilled water system, we want to do that in the chilled water return. If it's a primary, secondary, ideally before the decoupler loop. In a heating hot water system, especially if you're drawing through a heat exchanger or a boiler, you want to do it as you come out with the hottest water, but on the suction side of the pump.
Okay. Thank you. Got 2 more questions left. Several engineers in our market have been specifying buffer tanks, assuming they don't need an air separator. What are your thoughts?
There are 2 different purposes. The purpose for a buffer tank is to allow that system to have basically enough thermal inertia so the chiller or boiler don't overcycle. The buffer tank is not really there to remove air. Now, if they're looking for a component that is not just for volume only, if that buffer tank is somehow being used in hydraulic separation, things like that, we have our quad unit, that would be a separate discussion, that handles air and dirt elimination, but also as a low loss header and a hydraulic separator. Now, in some cases, we've had some people that have said, can I use that unit volume as a buffer tank? If you have enough volume, it probably doesn't have enough of that. But typically, I would not look at a buffer tank as an air removal device.
Okay, 2 questions left now. How are filters being considered for cleaning / repairing frequencies? In other hands, do we need redundancies in comparing them traditionally? If there's less, have there been considered in financial paybacks? Sorry, it's written a little broken.
No,
Does
that's
that
fine.
Okay, great.
No, actually, we're working with a customer now on that very same discussion, and we've looked at how long does it how often do you change your filters? How much does it cost? Let's look at do we already have them installed? Do we not? What we've seen is in this particular case, they might only their system is very, very clean, very good water treatment, very low particulates, and they might change their filters out once every 2 months. There are other facilities where we know they're changing those filters out once every 2 weeks, once every 4 weeks. And so we can look at that. That's something we can do to say, all right, let's look at a financial analysis of this or that. The nice thing about our unit is that if we're looking at a comparison, the only cost we have is just to blow down the debris from the unit. That's really not a cost. That can be manual or something else, but we can help look at that. We've done that with some customers, so we could probably help come up with something like that.
Perfect. And last question for you, Stephen. When would you specify a dual connection versus a quad air dirt separator?
A dual connection. I've seen some schematics of something similar to what I think is being asked. And that I've seen a couple of folks ask, can we do a custom type of a configuration? I've seen it and my comfort level is not there. So I think I know what's being asked. But that would be if somebody could get with me directly on that, maybe we can talk schematics. I don't want to speak out of turn if I'm not sure about the question on that one.
Okay, we can certainly connect you to after the webinar. Well, that's actually all the time that we have for the Q&A right now. So thank you so much, Stephen, for giving us your time and answering all those awesome questions. Thank you. I just want to close things out real quick by thanking Spirotherm, our associate member, for teaming up with us today. As a reminder to all the attendees about CEUs, you will receive an email in 1 week with your proof of attendance. And if you enjoyed this webinar, please visit energymgmt/training to keep up to date with all of our upcoming offerings. We have a virtual EMP seminar for experienced energy managers coming up, and also a free webinar on energy benchmarking. So thank you, everyone. Stay safe,
Thank you, everyone.
and we'll see you next time.
Thank you.